Good afternoon, everybody. Thank you for taking the time to attend this talk regarding measuring software quality. In this talk, I want to look at a number of different aspects associated with what we mean. But I want to start off very much with this idea of, this is a very famous quote from Minamoto, which is a Japanese swordsman who authored a very famous book called The Book of Five Rings. And in that, he outlines his broad principles of strategy. And there's a number of principles, 9 different principles, and the final one being this famous quote here, do nothing of which no use. I think that becomes important when we start talking about, when we look at software quality and start defining and measuring software quality, is why are we doing it? What is the value behind this particular software? In terms of getting into that, one of the things we need to think about is, how do you define software quality, or how do you define quality anyway? And the first difficulty here is that depending on your viewpoint, there can be quite differing models associated with this one. So if we look at ISO 9000, then it talks about the degree to which a set of inherent characteristics fulfill the requirements. And that's, again, from a sort of engineering or architectural perspective. We think about things like the V model, is this traceability with system test and user acceptance test back to requirements. And we talk about good requirements being testable. So that certainly gives us some inherent idea of quality. Six Sigma, very widely understood, very much, as you can see, comes from a manufacturing background, talks about the number of defects per million opportunities. You've got to question, how well does that sort of thing fit with a software model? If we compare Drucker, and Peter Drucker's well published in this area, and the American Society Quality Society, then the Drucker quote very much talks about this idea of the user-driven side. But the first thing we've got to stand back from and say is, well, can we separate out software quality from system quality when we're dealing with embedded systems? The system is the deliverable, it's what the end user is actually interacting with, or the system is interacting with. And historically, obviously, many embedded companies come from a manufacturing background and have a fairly good handle on manufacturing-based quality, so electronics, mechanical, and we can measure that sort of quality. And many of the procedures in place for many companies come from defining quality, such as Six Sigma, around that particular model itself. We look at embedded software saying, well, can we separate out the things? And I think certainly what we've seen is that a number of companies are now understanding that even though they may have a very good product, if the software itself sitting on that product is not functioning correctly, is not giving a pleasant experience, or is buggy, then it's impacting the perception of the overall quality system, where actually the main system may be very, very reliable, very good, but the software itself is letting this down. And the most extreme there is even something like an app, an iPhone app, not being part of the product. Now, again, this comes back to, how do we talk about quality, how does engineering? So here's I'm sure many people are familiar with the bathtub curve. This generally comes from, again, more of a manufacturing background, where we talk about reliability. And for most devices, we have a burn-in time, we have an early life mortality type time, where for a component-based system, hardware components, mechanical-based components, we can expect a certain amount of failure in that very. So we go through a test procedure to try and eliminate all of those early life failures. Once we're past that, then over the expected useful life of the product, there is normally a well-defined expectation of failure. So when you're trying to do failure analysis and mean time to failure type numbers, then you're using those particular factors. And then within most components, they'll become a wear-out time, so a breakdown of the device for whatever reason, where we start to get a higher failure rate. The problem here is, how do we apply that to software? That really doesn't fit. People have tried to fit this onto software, but of course, software itself doesn't have the physical aspects associated with this, so we can't really apply this curve. So we have to start thinking about software from a different perspective. Now, the simplest one, that if you'd say for most people, what's a quality count? We talk about bugs. Bugs is the easiest thing to think about, faults within the system. And we can look at this ratio in terms of how many bugs per n number of lines of code. So the typical here is either 1,000 lines of code or 1,000,000 lines of code. Steve McConnell's book, very, very good book, Code Complete. If you've not read it, I highly recommend it. A lot of very, very good information in there. And he brought out this information. Now, this is, again, a few years old, and it can be very, very difficult to get this information out there. But there he talks about the industrial average being between 15 and 50 errors per 1,000 lines of code during development. Microsoft published some papers a number of years back where they talked about 10 to 20 defects per 1,000 lines of code during in-house testing, and then getting that down to 0.5 defects per 1,000 lines of code for a released product. And at one time, I remember reading about Microsoft talking about on average, there were 3 testers per developer. And that's probably not an efficient use of time, but it's one way of trying to stop poor product going out the door. Harlan Mills, they pioneered this concept of clean room development. And with this technique, they've documented they got down to 3 defects per 1,000 lines of code during in-house testing, and managed to get down to 0.1 defects per 1,000 lines in a released product. And that's still, not insignificant when we can be talking of a million lines of code. So when we look at quality in software within Feabhas, we look at it we take a number of different perspectives. And the first one, which I think most people will probably be most comfortable with, is this concept of compliance using a standard. So this chart is taken from safety.net. It's not 100% accurate, but it's a fairly good analogy in terms of trying to think about the standards we use and the standards that are out there. Now, again, most of these are system standards and have a subpart with them to do with software. So sort of the grandfather of all these standards, granddaddy of all these standards, is the 61508, where we talk about safety integrity levels, and those different safety integrity levels come about to do with risk assessment. And the different SIL levels will recommend different techniques to be used when developing the system, and especially certain aspects of the software. And derived from that have been a number of sort of overlapping standards, looking at slightly different areas. So the automotive area, 26262, has the idea of automotive safety integrity levels. Medical systems have class-based systems. You can see rail, civil aerospace, DO178B and C down the bottom have levels. So within each of these, they'll tend to have subgroups within them, subsections within them. So if we take as an example, and we talk about ISO 26262, then within that, there is part 6 of that. So the 26262 is actually a road vehicle functional safety specification, and part 6 is the product development at the software level. Now it's interesting when you look at that. Here's one of those. This is one of the initial table within that particular subset of that particular part of the document. And it talks about coding and modeling guidelines. And the idea is it's giving people who are working in the automotive industry a set of guidelines towards how software should be developed. So this is giving us our compliance-based model. We're trying to tick the boxes. If we look at the second item there, the use of language subset. So out of this, we have MISRA C. MISRA C is a very well adopted, very good. The 2012 standard is a very, very good standard to work to, certainly for embedded C. And so by using something like MISRA C, so the thing about the standards, they don't say you have to use, for example, MISRA, but by using MISRA, you get it's much easier for the authorities to say, yes, you're applying these guidelines as such. And there's a number of ones in here, even down at the bottom, we have things like style guidelines, naming conventions, etc. Interesting, in the whole document, the actual term quality only appears 3 times within the part 6 document. So when you analyze it associated with it. If we look at that first one, enforcement of low complexity, what does that generally mean? And probably the easiest measure there and the most widely accepted measure is this thing called psychomatic complexity. This has been around since the mid-70s. You may have heard of it. You turned into the McCabe metric from Tom McCabe, who originally developed the metric associated. Very, very simple metric. And I say it's still my go-to metric when I'm working with business or doing consultancy. It's the first thing I always get companies to do on their code base. And it gives me some indication. So the basic principle of psychomatic complexity is looking at an individual function. So for example, an individual C function. And what it will do is do path analysis to then calculate the number of independent paths through that particular function. So it uses this unitless number of edges minus nodes plus 2. And the plus 2 is obviously because we have an entry and exit part. Now, there is a side effect of psychomatic complexity when you look at testing, is it gives you the upper band for the number of tests possibly need to be written to give you statement coverage. So just 100% code coverage, not decision coverage or branch coverage, just pure code coverage associated with it. So how do we calculate? So if we take a very simple example, we took a bit of code that would, typically there are tools out there, there are automated tools out there. So anybody using a higher order static analysis tool like QAC or LDRA or Covariety, these will typically calculate cyclomatic complexity automatically. And all they do is they do a generated graph and they will look for control structures. So it's very much driven by control structures, our if-then statements, our if-else statements, our switch statements, any iterations, so do, while do, and the for loops. And from that, we can see we get this sort of branching-based model. And based on this branching-based model, it gives us edges and nodes. So again, it doesn't take into account the complexity of a conditional statement. It's purely we have a true-false branch associated with it. So here's a simple piece of code, and you can see the cyclomatic complexity of this path gives us a number of 4. There are 4 independent paths associated with this. Now, when McCabe wrote his first paper, he gave the bounds, and he talked about if a function has a metric of 10 or less, then we can consider it a fairly simple program, a fairly simple function, and we don't have to worry too much about it. Now, note, again, this doesn't take into account a function calling a function. It's purely at the individual function level. 10 to 20, more complex, certain amount of risk. 20 to 50, getting complex. And then he said above 50 is untestable, very high risk. Now, cyclomatic complexity is not foolproof. Large switch statements, which again many C applications will have, and certainly nested switch statements, will very quickly skew this number because every case label within a switch becomes a separate branch associated with it. And again, different tools sometimes will give you slightly different values for the same bit of code. It's the way they may interpret switch statements, the different case labels in the switch statement, for example. Now, over the years, again, I've collected this. What I'm looking for typically is the company to give me a histogram where we look at the number of modules, the number of functions that have a particular value against that particular value. So ideally, we have a lot of functions with low cyclomatic complexity, 1s, 2s. And we should hopefully see a very quick drop off as the number goes up. So we want a short tail, and ideally that tail to be below 50. But typically what I see in many code bases, especially code bases that we could say if we wanted to talk about quality relating to complexity, is that the drop-off of the numbers is very slow. So we start to have lots of modules with numbers with complexity above the 20s, for example, and certainly getting well above the 50s. Now, my record over the years, I've been collecting this. 2 years ago, I had a new record with a company I was working with, and they managed to generate a single C function with a complexity of 1,328. During the seminar this morning, it was quite interesting that somebody came back and said they have a function in their code base with nearly 2,500, which is just staggering to think of. If you're not doing it, highly recommend you do this. There are open source tools. There's a very good one called Lizard out there. But if you're using a static analysis tool, which I hope you're doing, you've probably already got this available. It's also something a lot of tool companies now are using as part of their build pipeline. So if they're using something like Jenkins, they'll actually use it as a gate in the build that if the complexity is getting above a certain level, it won't continue the build. And that's a very valuable thing to be. So that's our compliance-based quality. However, another completely different perspective we have to be aware of is customer perceived quality. And this is very much the badge, certainly more for commercial-based applications. Then this is a big driver naturally, is how well people perceive the product. And we can have the arguments of iOS against Android, and you have what people tend to call the fanboy models. You take a particular brand, and you will argue, and people will argue for hours on the web about which is better, which is the better product and a better quality. And of course, there's a high degree of subjectivity in here and reflections of how people like this product. And sometimes this can be referred to also as extrinsic quality as well. And for commercial companies, this is naturally going to be highly important. It has to drive that particular product area. So that's our separate one. So we can build a very compliant product, but of course, if the customers don't perceive it, do they care when they're buying, for example, a car? At the badge level, do they compare how well it applies to something like ISO 26262 within that? We then have a further viewpoint we can talk about, and this is called intrinsic quality. And I'd say if you ask most engineers, most people certainly writing software, for them to try and define their viewpoint of quality, then it's likely most of the terms they will use will relate to intrinsic quality. And some of these can be very subjective. So, for example, readability of code. You can look at code and saying, well, okay, certain language lend themselves better than others, but there's no reason we shouldn't write readability. So we certainly have readability of code. Fundamentally, this is probably more about the architectural design issues, how well it's constructed. And again, different people, depending on the background, will have different viewpoints associated with this. So these are three strong viewpoints. We have the intrinsic quality, what I'll call the engineering-led view of quality, and if we use terms of how we would probably define it. We have a compliance quality, which is typically if we're going to be in the safety critical world or high integrity, and of course today more security centric, where they're trying to, and good compliance will naturally reinforce intrinsic, and that's generally what a compliance quality model is trying to do, is help improve intrinsic quality through a set of rules of saying you must do these particular things. And then we have the customer C quality associated with this. So there are three viewpoints of quality. But the problem is, if we're not careful, and depending on our company, there can be a lot of danger of overemphasizing one. And of course, you can guess within different aspects how this is going to affect us. And if we're not careful, if we overemphasize one, then it can commonly be detrimental to the other. So take some example. If we overemphasized the compliance-based quality, then we can run a particular danger. So compliance is, you become a slave to the process, in the fact that whatever we're going to do, we just are ticking boxes. And I've worked with companies where at the management level, their only interest is, are they fulfilling compliance? Are they ticking the right boxes associated with it? And that, again, doesn't necessarily mean we're going to get good software out of this. And because that's so much dependent on the particular process, the particular compliance model we're doing. The biggest issue I certainly see here from a quality perspective is it means that software people don't end up owning the software. So they don't feel responsibility for the software and the processes. And once they don't have the responsibility, then the quality of the software becomes somebody else's problem. So ultimately, we talk about saying, well, I'll throw my software over the wall, and it's the test group's problem, or it's the QA problem. It's not my problem associated with that. So we have to be very aware of compliance. Now, of course, the counter to that, and the complete reverse of that, is where we have a commercial environment where we're completely driven by the customer. And a lot of this, of course, has been backed up by the Agile model. The Agile model is very much about customer first associated with this. So it's very much about the feature, the features, I always talk about how shiny is the product. And this can be driving from a quality perspective is how quickly do we get the product out. Now, I came across this term, I was introduced to this term, a very good book called Winning by Design by Westwick and Cooper. And they introduced this term called the promise point. I've not heard of this before. So we think about the delivery point, when we've got to ship, we've all got pressure to ship, and that's ultimately got to get it out the door. But the idea of the promise point is saying that this is when we announce what we're going to ship. And we make a promise. Now, you get this on a microcosm with Scrum. I see this happening even within Agile, when Agile starts to work, is that the promise point and the delivery point, there is a time frame between those two. And once we promise something, there then becomes pressure to deliver. And once we have pressure to deliver, then it can erode quality. And it erodes quality typically by bypassing and cutting corners. So I've seen, again, management saying, well, reducing the amount of testing. We just need to get it out the door. So the difference between the time between the promise point and delivery point can be quite critical to the pressure that's going to be placed on the engineering team. Now, I use one of my favorite stories is I look back at when the original iPhone was Steve Jobs was on, and we all knew it was coming to an extent, but he was on the stage talking about it, and he said, announced the iPhone, they did the presentation, and then he goes, and this is going to be available next week. So that's his promised delivery point. And what that means is that the engineering team had a huge amount of time to iron out most of the problems. So even though it wasn't a faultless problem, it was still a pretty good product from the quality. Now, anybody who has followed Apple over the last year or so has seen that those pressures have changed. We're now seeing products that you could argue are not the quality they were. And this is because this promise point, delivery point, is starting to broaden. Now it can be months associated with this. So this is a fact. And again, even like I say, this can happen at the microcosm level to do with Scrum and Sprint. And Agile, again, has driven a lot of this. Now, this was a tweet that came up last year on Twitter naturally, from James Grenning. So James is one of the original signatories of the Agile Manifesto. Written a very, very good book regarding the test-driven development for embedded C. So again, I'd still rate the book. I think it's a very, very good book, and I know James personally. But he pushed this out, and I had an immediate reaction to this. So Sally Globe at the time was she was head of quality at the Guardian newspaper in the UK. She subsequently moved on as senior engineering manager to Deliveroo. And she was doing a presentation at a conference called the Continuous Delivery in DevOps in Copenhagen, which is what that hashtag is representing. And her presentation, she's written a couple of blogs about this. Perfect software is the enemy of rapid deployment. And of course, this is the Agile model, this whole model of moving towards continuous delivery and continuous deployment within that. And her tagline is not wrong long. And that's, and again, as an embedded person, I certainly had a reaction. I'd be interested to see your reaction to that as well. And like I said, the Agile community are very much pushing this idea, this ability to do very rapid updates. But part of that, there are two issues that come out of that when we start talking about quality. We're very customer driven. We want to get these updates out there. So first off, again, quite an interesting read. This was on LinkedIn. Your software may be lousy, but at least it is Agile. And actually, after the talk, we'll be sending out a document with all the links to these original articles for you if you want to follow any of these up. And what we see here is if we drive this very quick, very reactive model, this not wrong long model, is we have a massive danger of not dealing with intrinsic quality. We end up with very poor architecture. So there's no proper planning from an architectural perspective. So bizarrely, we can actually end up with very fragile products. So we can fix them very quickly and we can be very agile, but we have to because they're actually not inherently and intrinsically well-defined associated with this. And also going back to people, the Agile community, especially who are pushing this not wrong long, is saying that if you're software as a service, you're a website, then possibly you can do with that. But once we move to physical products, especially modern day, and of course IIT is our poster person at the moment, is how if we do over-the-air updates, and of course that's one of our big nirvanas, is can we rapidly push out over-the-air updates? What if it goes wrong? So here's another classic example. Went out in a threat post back in August of last year, and this was a smart lock, a Bluetooth-based smart lock. And the manufacturer Lockstate managed to push out an update which bricked the device. Now, of course, we all know the problem. And the bit in the note says customers are asked to either return impacted locks for repair or request a replacement product, request a replacement. And this is not great for a lock, especially as it was left in the unlock state associated with that. So when we're dealing with applications, then yes, bugs do matter associated with that. Okay, so that's looked at compliance-based being the leader and customer-led being the leader. But what about intrinsic? So what do we mean by intrinsic software? So as I said, intrinsic software is this software engineering, this engineering-led view of software. And what we're really dealing with intrinsic software is we're thinking about when we're designing software and re-architecting it, is we want to make it resilient. We want to make it robust. So we want to make sure that when we need to make change, we accept there's going to be change. It may not be because of our problem. I mean, given the the things like the recent Spectre faults show an example that we may be completely out of control of the need for change. So we know there's going to have to be change. We have to adapt, and I think that we can take things from that Agile community. But to build a good architecture is key to this ability to update. The problem is that how do we view this cost of architecture? Naively, is the cost of modification is fixed, there's no effort. But of course, as the world changes around us, then there will be a time. So sometimes we talk about software rot, we may talk about technical debt is the other phrase that's used for this, is that will become a point where the software we have will have to be changed. Now, for a product that has very short lifetimes, then this may not be a problem. That the infrastructure it's built on may not change quick enough that it's a problem to us. So taking a very good example that's affected a lot of people is the impact of things like secure sockets, TLS, is that the changes within that, when there's been bug fixes within TLS, that can have a massive retro effect approach on that. And if we haven't got a good architecture, that's going to cost a lot more to do that. So even recently, I was told anonymously about a project where the overall cost of change has ultimately, because of the lack of software quality, has cost the company £15 million to fix the fundamental firmware issue associated with that. Now, the problem here is that it's a cost, and it's almost a hidden cost associated with it. And if we continue to try and gold plate products, as an engineer, we always want to do the best job. We want to build and build on build. We can end up with this particular model here. So hopefully you're familiar with this. Most people maybe recognize this building from Barcelona. It's a Familiara. And this is one of these beautiful, perfect building. Everything about it when you go inside it is perfect. But it was built in the build was started in 1883. And it's still not complete, and there are debates of whether it will be done in the next decade or next 2 decades. So this is sort of the analogy to trying for engineering-led qualities. We always want to add on. We always want to improve it. We always want to make it better. And in that case, we can be in danger of never finishing it. And again, this is the thing that can drive management crazy. Is when asked how close we are, we're always 80%. Close to being complete. So there are 3 viewpoints of quality, but we're missing one. So we've got compliance, we've got the customer-led, and we've got the intrinsic. But at the end of the day, we've got to also address fitness for purpose. So now, again, when I first researched this, and I'd seen this image before, and I sort of said, okay, this is a great example of fitness for purpose. The Swiss Army knife with 1,000 blades or whatever. It's actually a Wenger knife, not the Swiss Army. I thought this was just a computer mock-up. This actually is a real product, and actually quite a collector's item now within that. And I think most people would hopefully accept that this is probably not generally fit for purpose. I'm sure for some people, it's got every whistle and bell. And this is sort of where marketeers start defining requirements, is we can end up with these sorts of products that we can build very good products, very compliant products, but we're not being customer-led. If we're not careful, we're marketing-led associated with this. So once we start trying to say, well, how do I measure quality? The difficulty is quality itself has all these multifacets associated with it. And we can't just use a single measure. We have to ultimately balance all of these things. And some of them are incredibly difficult to even try and measure. How do we measure certain aspects to do with intrinsic quality? So compliance is probably the easiest to measure. They're the ones when most people talk about quality and will start talking to you about quality. They'll generally be down the compliance-based model. And we can do a certain amount there, certain static analysis aspects we can apply, certain test analysis we can apply, but there are certain other parts which are very difficult. So the architectural design is very, very difficult to view from that point. And again, even if we build very good intrinsic quality with good compliance, then how does our customer perceive it, and ultimately is it fit for purpose? So within all of that, what I'm really coming down to is that the trying to measure quality is incredibly difficult. It fundamentally becomes a business choice. But when you start thinking about quality, so what I say after this, think about for the product you're working on today, what does quality mean? What is the acceptable bar for quality within your business? But you have to think about all of those different facets. You can't just think about intrinsic qualities you would do necessarily as an engineer. We have to find this balance between the 3. And the problem is quality costs money. And this is a real difficult thing, because how are you going to ultimately demonstrate any sort of return on investment, especially for things like intrinsic quality? It can be really, really difficult if you want to invest in tools, in static analysis tools, in test tools, is how can you demonstrate? And typically where we see companies address quality is where they've been burnt. There's something they've had a major problem. This quite often will demonstrate itself or manifest itself with a delayed release in a product. So I've seen very brave companies where they will pull a product release because somebody has ultimately managed to stand up and saying, this just isn't good enough. I know one company, for example, delayed a product release for a year until they felt that, and this was purely down to software quality, that the software quality was at a point where the business leader as such felt that it was good enough to go out to the market. So you need some sort of quality bastion there who's going to stand up and be able to balance these particular aspects associated with it.